Okay, so last time we had a look at typing rules for a variation on the theme of imp. If you remember, what we did was we smashed the grammar so that we weren't using the grammar anymore to tell integer expressions and Boolean expressions and commands apart, and instead we decided to do it with types. And that immediately began to free us up a little bit, because, for example, we can now cheaply have if for any kind of thing, not just for commands. So here we said for an if to be all right, we have to check if the condition EB is a Boolean. That has to be a Boolean. But we don't really care what the then branch and the else branch are, as long as they're the same, because you could get one or the other. They have to be used in the same way. And then the whole if has the same type as both branches. So that means you can use an if to decide between two numbers, you can use an if to decide between two Booleans, as well as using an if to decide between two commands. We also liberalize things with assignment and variables. Before, we were restricting it so that you could only store numbers in variables. And now we're saying you can store anything in a variable. And the type system uses this judgment. Gamma says X accepts things of type tau. So that means, so gamma is the context. It tells you the types of the variables that are in scope. So it's doing the bookkeeping for which type of thing is allowed in which variable. So if the context says yes, X does exist, and the most local X in scope will accept values of type tau, then if we have an expression of type tau, we can evaluate that expression. That will give us a value that we can store in the variable. And we said that the whole assignment has type void. That's to say, an assignment is just a command. While it's executing, it generates a value and puts the value somewhere, but it doesn't itself return a value. That's a choice, by the way. So I don't know if you learned a bit of C last year. In C, an assignment also returns the value of the expression on its right-hand side. And C programmers use that to write extremely confusing programs that are very, very short and look like total line noise. Yeah, it's that's a choice. So we should try and knock this on the head today. Basically, my target for today is to communicate the things you need to know to do the homework. I had a copy of my notes somewhere, maybe there. Ah, here they are, at the bottom of my pile of scrap paper. Okay, so there are some things we should look at as far as more typed imp is concerned. If you remember, I left you with a cliffhanger. You can see the typing rule for if there. I asked you to think about what the typing rule should be for while. Let's do the boring bits. There will be a context that tells us the types of the variables. And then there'll be a while with a Boolean condition, we hope, I suppose, and a loop body, and that thing better have a type. And we're going to require that the condition has some type, and we're going to require that the loop body has some sort of type, and we should have a little think about what these might be. Okay, so the condition. What type do we think the condition has? Bool. Yeah. So remember we got three types. We got void for commands. We got int for numbers, and we got bool for Boolean values. We definitely want the condition in a while loop to be a bool. Okay. Here's next question. What type do you think the whole while loop should give back? Yeah, we don't have a choice there. In particular, given that if the condition is false, the loop body will not even execute at all. We can't make use of any information from the loop body to tell us the type of the loop. So we have no real choice here. The while loop is definitely a command. It gives back void. Now, we do have a choice when it comes to the type of the loop body. What do you reckon? We could allow it to be anything. It doesn't really matter what it is. All we're going to do is, if the condition is true, we're going to evaluate it. And the type overall of the while loop says, even if we do evaluate it and it does produce something interesting, we're going to throw that away. So it would be weird, but we could just say this is allowed to be anything. I think it's more sensible, given that whatever it is going to be thrown away, to insist, doesn't do any harm, and it's tidy, to insist that the loop body is also just a plain command. Okay? So we've got this contrast between ifs that can be of any type you like, because we know that we're definitely, assuming we get as far as evaluating the condition, we're definitely going to pick one of these two and evaluate it. So we'll, either way around, we've got something that claims to be of type tau, we can give back something of type tau. Whereas in a while loop, doing nothing, if the condition is false, is very definitely an option. So we better leave it as a command. Does that make sense? So often, if and while are quite like each other in that they both involve testing a condition and then deciding what to do. But here we've exposed a bit of a difference. All right, we should do some other constructs just to make sure we're in shape. I don't know if I'll do everything, but I'll certainly do new. So now we just have one new construct. We used to have new for integers and new for commands. So we've got new x is E0 in E1. What sort of a thing is that? Well, let's just think it through. We need to figure out, so that let's remember what it means. We're going to use the value of E0 to initialize a local variable called x. So we need to think, what type is that variable going to have? Well, if we know what type of thing E0 delivers, that thing is going to end up stored in x, so we better make sure x gets that type. Okay, so our first move is to figure out the type of E0, which I'm going to call sigma in lowercase. Okay, and then we got to bring a variable into scope for E1. So what happens is that the context gets extended by x in sigma. And that means that E1 is allowed to monkey about with x. It also means that any earlier x in sigma is going to be hidden from E1. Right. I mean, if you happen to use to choose the same, a variable name in a new that already exists, you are shadowing the previous one. Note there's a convention here that when you have local scope, the local stuff goes on the right-hand end of the context. So you can think of the context as telling you a history of when things came into scope from left to right. It's really time is going left to right here. This is the most recent variable brought into scope. Okay? And our rules, I'll just stick them back here, for figuring out what type things are, looking variables up in the context, respects that the one on the right is the preferred one. So this rule says if x in tau is on the top, then x has type tau. And you only look further to the left if you don't find what you're looking for on the top. Sometimes I call it the top, sometimes I call it the right. I should really call it the local end. If the most local thing is not the thing you're looking for, then you look further out. See, out, left, down. Yeah. Spatial metaphors are sometimes problematic. Okay, so we got as far as x is in scope for E1. Do we care what type E1 has? Well, only up to a point. We're certainly not going to be picky about it. So we'll just say it could be anything. I mean, that after all was the point, right? We wanted, instead of having a separate new construct for integers and a separate new construct for commands, we want to have one new construct that does all the jobs. So it doesn't matter what type E1 has, except that, of course, that's going to be the type that we give back for the whole thing. Okay? So we have generalized new for integers, new for commands in two ways. One, the same thing does both. Two, the variable can have whatever type we like, not just integer. And so, for example, we can now write new in Boolean expressions as well, if we want to. So doing this with a type system rather than grammar allows us to offer a lot more flexibility. So is this making sense, even though it's got some Greek letters in it? Okay. Cool. That was new. I'll do one more, I think. So in the past, we had separate typing rules for plus and minus and less than and all of those sorts of things. And I'm going to try and knock them off in one go, or at least abstract out the common pattern. So in general, when you use an infix operator, it looks like that. Yeah? So how do we kind of extract the essence of what's going on? What we do is this. We say E naught gets a type that we're going to call sigma naught, and E1 gets a type that we're going to call sigma 1, and we're going to say the whole thing gives back a type tau. I haven't really said anything like this. At the moment, this says like all operators can do anything, right? Which is bullshit. So let's make sure that operators behave sensibly. What we do is this. We have to add a constraint. Haha, I haven't told you what sigma is yet. I'll tell you what sigma is just now. So, sorry, another Greek letter. Sigma stands for signature. And a signature just means a collection of operators where we just know what they all do. So what is this signature? Well, you can see we're checking whether this quadruple of things is in the set. So it's a set of quadruples, each of which looks like an operator, two input types, and an output type. So now we just say, so the sigma is a parameter of the language. If we want to chuck more operators in, we just throw more things into sigma. So for example, we'll have plus, int, and similarly minus, we'll have and, bool, bool, bool. We'll have a whole bunch of other stuff, less than, int, bool. So just a whole big lookup table of all the operators we know about, just a catalog of them with their types. One thing we're allowed to do, which is perfectly fine, is if we've got an operator like equality, we're allowed to say that that has type int, bool, and we can also chuck an entry into the signature for bool, bool, bool. So when you give an operator more than one entry in a signature like this, that's called overloading. This basically says you're allowed to test integers for equality, you're allowed to test booleans for equality. And once we've done, of course, you use different algorithms for testing whether booleans are equal than you do for testing whether integers are equal. So here, the type checker is making a small contribution to your program. You just write an equal sign, and when it does the type checking, it figures out which algorithm you need to put in to test that equality. So in a very small way, when you have overloading, the type checker is filling in bits of your program that you couldn't be arsed to write. So remember that types are not just there to say no to you. Types sometimes fill in useful little details that you can't be bothered with. So that's very handy. So you just make so instead of having to write a rule for each operator, we've boiled it down. There's one rule, and then there's just a big catalog. That the rule says look the operator up in the catalog. Is that making sense? So it's just a more compact way of presenting a whole bunch of rules that look very, very similar. All right. Okay, so that's pretty much it for what the type system is. But remember, last time I said whenever you have a type system, there ought to be a payoff. There ought to be some answer. There ought to be a deal, you know, that is like, you play by the rules and life will be nice somehow. Otherwise, why would you play by the rules? I mean, maybe you're just a saint or something, but we ought to be able to say something about what the benefit of being well-typed is. You know, what kind of nonsense doesn't happen when your program is well-typed. You know, Milner's slogan was always, you know, well-typed programs don't go wrong. What do we get here? Well, I should also think a little bit, because we had a big step, dynamic semantics for untyped imp. So we ought to have a little bit of a think about what the dynamic semantics for typed imp is like. And it's pretty similar, but let me just write down at least some judgment forms. We need, in general, a judgment form that says if we start with some store and some expression, that will evaluate, giving us a new store at the end, because some variables might have changed, and a value. So we'll need something like that. Now, we used to have a separate evaluation judgment for commands that didn't give you a value back. We don't need that anymore because commands and expressions have now merged. But what we do need is to create a special value. So our values, they're all thrown in together now. They look like true or false, or a number, an integer, or we have a special value, which is the boring value that we pretend commands give back, which some people, you can pick any symbol we like for it. It's common to call it star, even though it's really boring. So the star is not a celebrity in this semantics. And we can also say what types values have. Clearly, true and false live in bool. Integer lives in int. And star's job is to be the value in void. Okay, and then we can use the same evaluation judgment for evaluating integers, integer expressions, Boolean expressions, commands. And all the rules you've seen before can be fitted into this. Where previously you had this command executes leaving this store rule, you just say this command executes giving this store and the value star. Yeah, so other than that, everything pretty much stays the same. We have to be a little bit cunning with blocks, but not very cunning. Might write the rules for this. We say if you start with a store sigma naught and v naught is the last value. I've been writing that as a backslash in my notes. No, I haven't. I've been writing that one as a vertical and this one as a backslash. If you start with a store sigma naught and v naught was the last value you saw from a block, if you evaluate the rest of the block, you will end up with a final store and the last value. Remember, we said in a block, if a block is empty, it has type void. If a block is not empty, it has the type of the last thing in the block. And that means we have to give back the last value in the block. So let's just check what the rules should be. We will have a rule that says if we start from sigma naught and our command looks like a block, then what will we do? We will start running the block. We will say that the last value we've seen so far is star. We'll run the block. If that gives us a new store and some value v, we'll give back that store and the value v. So we always kick off the execution of the block with the last thing we saw was boring, right? And that way, if there's nothing, well, okay, here's the other rules. Sigma naught v, if the last thing we saw was v and the block is empty, nothing changes, and v was the last thing, so v is the thing we give back. Otherwise, what happens if we have at least one command in the block? What do we do? Well, we evaluate the first expression in the block. That will give us a new state and a value. That value is now the last value that we've seen. So when we kick off the rest of the block, we start in store sigma 1. We don't throw away our changes to the memory. V becomes the last value seen. That's a vertical, that's a backslash. We're going to run the rest of the block. That's going to get us to sigma 2 and some value v prime, and that's our end of story, sigma 2 v prime. So everyone see what's going on there? We're just keeping hold of the most recent value in the block that we computed so that we can give back the last one. And we thread through the stores so that the updates that happen when we evaluate the first expression, we keep a hold of them and use that store to start off the evaluation of the rest of the block. Okay, I should say something about, so that's those two. The other two, which are not terribly exciting, you could probably figure them out, is I have a judgment which says if you look up a variable in a store, you can get its value, and a judgment that says if you assign a variable to a value, if you know, in an old store, you get a new store with that variable changed. Okay, those are the other two things, and then we can say what the evaluation rule is for an assignment. Suppose we are evaluating this assignment. How do you evaluate an assignment? You evaluate the expression on the right-hand side. And then you update the store by putting the value into the variable. Right, note you can't put the expression into the variable, you can only put a value into a variable. Which store should I update? What should I put here? Yeah, sigma 1. That's to say, because we can have all sorts of stuff going on when we evaluate an expression, this store sigma 1 really can be different from the one we started with. So we make some changes while we're evaluating the right-hand side of the assignment, and then we finish by actually making the change that corresponds to the assignment itself. Okay? What value should the assignment give back? Well, what type did we say that an assignment has? It has type void. So what value should we give back? Star. So you can see exactly what happens to the value. It gets generated by evaluating the expression, then it gets shoved into a memory location, and then the assignment itself gives back nothing. Okay. So we've got some dynamic semantics. Just slightly adjusted from what we had before, but everything else behaves the same way. Do you think we can make any promises about the behaviors of things? So what happens if we know that an expression has a type? What can we say about those things? It's a slightly tricky question. Well, first of all, if we want to make any kind of progress, the expression E doesn't exist in isolation. It expects some variables to be in scope. So we would want to check that the initial store makes sense with respect to that. So we can also write down a system of judgments that say when a store fits in a context. There's two rules. One of them is Zen-like. So the empty store is a perfect fit for the empty context. And then if store sigma fits context gamma, and V has type tau, then sigma with X equal to V fits in gamma with X in tau. So all we're doing is checking that the entries in the store match up name by name and type by type with what the context tells us to expect. So let's impose also the condition that sigma naught is a fit in gamma. If we know this bunch of stuff, what should we expect? What do you think would be, so we're saying, suppose the expression has a type in a context and the state we start in fits the context. And suppose that it does indeed evaluate, reducing a final store and a value. what do you think is true about the final store? Yeah?
That it contains a value of type tau?
Well, it doesn't necessarily contain a value of type tau, in that I can evaluate the expression 3 in the empty context,
Yeah.
but we certainly end up with a final store which might have different values in it, but because of the way new works, remember, new introduces a variable for a while and then throws it away again. So we know we're going to have exactly the same variables we finished with as we started with. And what's more, because all of our assignments make sure that you only put the same type of thing into a variable as was in there already, we are sure that if this is so, that the final store will still fit the context. And if you think about it, that's terribly important. We actually want the store all the way along through the whole execution to fit the context. Otherwise, the type system's useless, right? You know, if the type system assumes that the types of variables stay the same all the way along, but in fact there's a way that variables change what type they are, then we're in trouble. So you'd want this to be true. You'd also perhaps want some guarantee about what sort of thing V is. I mean, it's V that we would like to have type tau. So this property is called type preservation for hopefully obvious reasons. It says, you know, if the type system tells you that your program has a given type, then what you get out when you actually run that program, you know, really is, I mean, it'd be kind of weird if the type system told you that your program had type integer and what came out was not a number. That would be kind of annoying. So this we can deliver. You might want to deliver more than this. Specifically, you might imagine that you would have the property that if you have a context in which E has type tau, and you have an initial store that fits that context, you might like to promise that the expression will definitely evaluate. However, we cannot make that promise. Why not? What else might happen other than the thing evaluating? What can imp programs do if they don't stop? How do they not stop with a value?
They loop forever.
Yeah, they loop forever. Now, we have ruled out a whole bunch of shit, right? We have ruled out what happens if you add false to 17, right? Or try and do, 3 or star. We've ruled out data incompatibilities. So we can promise that if the program doesn't evaluate, that's because it's still going. And we can even, I do this in the notes, but I'm not going to do it here. I explore how to set that up and actually frame that property. What you do is you add to the dynamic semantics an extra little bit of information, which is basically how long you're willing to wait for the goddamn value. And you put in a default value that means I'm out of time, we've run out of electricity. And then you can prove that a well-typed program will either give you a value of the right type, or it will run out of time. And either way, the store, when it either gives you the value or runs out of time, will still fit the context. So you can make that promise, but you can't promise it'll definitely work. Okay. So I kind of want, I've got about 5 minutes. I want to say just something back over in lamb land, because I know we've got some questions about finding types for lambda terms, and I know there's been some mystery caused by, well, these two rules, our favorite rules. I sometimes write this as a lambda and sometimes as a backslash. Right. So there's a genuine mystery. If we think of these rules as telling us how to figure out a type, that's to say, if we think of the type as an output, then the lambda rule is dodgy, right? Because you don't know the type yet. You're trying to figure it out. Somebody just gives you this function, and all of a sudden, magically, from nowhere, we guess the correct type for the variable. This sigma appears from nowhere and goes into the context. And then we figure out the type of the body, and then we can give back sigma or tau. But the eureka step is just magically guessing sigma. So maybe we say, okay, tell you what, that's not what really happens. We actually tell you the type in advance. And we just ask you to check it. Then this rule's fine. All in, if this was given, we would know what we have to check in the body. But then we're screwed down here. Because if we're just checking this type, we only get the tau. We don't know what type to check for the function. Again, this sigma, if we're thinking of the types as being given in advance, we're given tau, we don't know how to pick sigma to check the pieces. So either way, whether we're checking types or synthesizing types, there's missing information in these rules. So what the hell does a computer do when it's given the task of figuring out types for these terms? Well, I'll tell you what it does. It does what we all do when there's a thing we haven't figured out yet and we have a little bit of mathematical ability. We call it x and hope to figure it out later. And we don't just read x, we need an infinite supply of possible stuff, names to call things we don't know. So what we do is formally we add a notion of unknown type to our language of types, essentially to use as variables that stand for things we haven't figured out yet. And then we figure them out by using the demands the type system places on them. So what we do here, if we're trying to figure out this type, what we actually just do is we say, I don't know what x is. So I'm just going to stick a variable in. I'm just going to call this $0. It's nice to put a number into your type variable syntax because you can always pick a fresh number. Every time there's something you don't know, you can always make up another variable name. If you just remember how many you've invented so far, you can pick the next number. And then we're going to hope that when we type check t, we're going to learn from the way t uses x more about what question mark naught has to be. So you can see, for example, when we are checking an application, we're now going to figure out a type for the function. If what we get back for f is just question mark something, then we've learned something because we know it's being used as a function. So if here you get question mark 0, you've learned question mark 0 has to be a function type. What do? You don't know the source type, you don't know the target type, so you say, well in that case, so if this turns out to be question mark 0, you say, well in that case I will solve question mark 0 to be question mark 1 arrow question mark 2. You know, I'll just make up 2 more variables for the 2 things I don't know, but at least I can solve for the first one. I can solve for question mark 0. And then the other thing that happens here is, oh, whoops, I forgot S colon. You figure out the type for the function, you figure out the type for the argument. The source type of the function has to be the same as the argument type, which means you now get an equation to solve that has variables in it. And the rules are dead easy. If you're trying to solve this arrow, you know, something, if you're trying to solve sigma equals, sigma arrow tau equals sigma prime arrow tau prime, the only way that can be true is if sigma equals sigma prime and tau equals tau prime. So you just solve, when you're solving equations between types, you just solve them piecewise. If you're ever asked to solve, you know, nat equals sigma arrow tau, you've had it. That's never going to have a solution. That program's going to be wrong. The other kind of equation that you cannot solve is something that looks like, if somebody asks you to solve question mark 0 arrow something like that, where you've got an equation you're trying to solve says that a variable equals some bigger type that has that variable as part of it, because then the type would have to be infinitely large there's no solution to this equation. So there's only 2 things that can go wrong, which you're familiar with: having a number where you want a function, or having a constraint like this where the variable you're trying to solve for is strictly inside the type on the other side that it, you know, has to be equal to. So there's, you know, stuff on that in the notes. Might talk about that a bit next time. I should kick out, except just to say the process of taking types that, or indeed, you know, any kind of syntax with variables that stand for unknowns and solving equations between them, that process is called unification, which is always a fun thing for an Irishman to talk about, and why I'm wearing a green t-shirt. So the idea that that computers can just, you know, if it doesn't know a type, just throw in a variable and then solve the equations later in order to figure types out. That was Robin Milner's big idea in the 70s for how to make good type systems for programming languages, and we're still doing it. All right. So hopefully that's you a bit more underway on today's exercise.